Log on, tune in, find out. Another good idea from Cambridge.
So my talk is entitled Is the Universe Designed? And I start from this headline in the Times, Hawking, God did not create the universe, which appeared on the 2nd of September 2010. And there's a big article in the Times, and the claim is based on Hawking's book, co-authored with Leonard Mlodinow, called The Grand Design. I should preface what I say by saying what a remarkable and amazing scientist Stephen Hawking is. He just celebrated his 70th birthday, was at the big conference over the last few days. Sad to say Hawking was too ill to attend, but it's a remarkable achievement, getting to his 70th birthday and achieving all the things he has. But that's not going to stop me making a few criticisms, particularly when he makes statements like that. Well, anyway, in the book, he says there is no need for God to light the blue touch paper and set the universe going, which he seems to see as the only role for God anyway. He says that philosophy is dead and has been superseded by science. He says that something called M-theory, which I'll have a bit more to say about, is the ultimate physical theory of everything. And he says that because there is gravity, or the laws of nature, the universe creates itself out of nothing. And he says that a multiverse, a giant collection of universes, explains the so-called fine-tuning, the special character that this universe has. Well, the statement that philosophy is dead is on the first page of this book. Yet only a couple of pages later, Hawking says that he adopts something called model-dependent realism. And if that isn't a philosophical position, I don't know what is. And indeed, it's a rather odd philosophical position, because one might ask, how does the reality of the world, the external world, depend upon the mathematical models we construct of that world? Hawking defines his concept by saying that it is pointless to ask whether a model is real, only whether it agrees with observations. If there are two models that both agree with observation, then one cannot say that one is more real than another. He is almost becoming an anti-realist philosophically here. And I mean, in contrast, someone like John Polkinghorne would adopt a position called critical realism, which starts from the reality of the world and says that, of course, we can only have an imperfect grasp of that reality, but it's one which we are getting a better and better grasp on as science progresses. So despite what Hawking says, philosophy, this is really a philosophy book rather than a science book. Now what I'm going to do in the talk is to go back to the Big Bang, describe it a little bit, and describe what this fine-tuning is, the special nature of the universe, and look at possible explanations and why people invoke a multiverse as an explanation, what it means to have an ultimate explanation for the universe, and to give a little brief history of cosmology, as to describe how cosmologists have alternated between different kinds of explanation, some of the problems for multiverses, and compare the possible explanations for the universe. Okay, well, this is a great picture in my view. I'm sure everyone in the room will recognize the person on the right. I might give you a prize of bar of chocolate if you recognize the person on the left. But he is actually a very famous cosmologist. This is Georges Lemaitre, who is the father of the Big Bang theory. He's a great cosmologist, and of course, as you can see, he's a priest. He was a Roman Catholic priest. He solved Einstein's equations of general relativity and came up with an expanding universe solution back in 1927. In 1931, he refined that and talked about the universe right back at the beginning being contracted into what he called the primeval atom, which subsequently got dubbed the Big Bang. In fact, the term Big Bang was used first by Fred Hoyle, the Cambridge astrophysicist in a radio broadcast, and it was used as a term of abuse, because Hoyle believed that if the universe had a beginning, which the Big Bang theory seemed to indicate, then you might need God, and that was a big problem for Hoyle, as indeed it is today for Hawking. Okay, well, in fact, the Big Bang theory is extremely well supported by evidence. It was predicted by Lemaitre from Einstein's equations. We have the expansion of the universe, which has been observed. It was observed, there was a bit of evidence for it by the time of Lemaitre's first paper, and much more a couple of years later, with the observations of Edwin Hubble. And that wasn't enough for Hoyle. That alone was not enough for Hoyle, who came up with an alternative theory to explain the expansion by saying, well, maybe the universe is really the same at all times and in all places, and in the spaces created by the expansion, as the galaxies move away, new matter comes into existence, and new galaxies are formed, and the universe is really eternal. It's a mistake to think of it as expanding from an initial beginning. Okay, well, there's been very important evidence come in since the expansion itself was observed, and I'm going to give you, I think, 3 examples. Yes. The major one, which was the killer for the steady-state theory, is something called the cosmic background radiation. This was predicted as long ago as 1948 by a group of physicists in America, colleagues of George Gamow. They predicted that the universe would have started off very hot, and as it expanded and cooled, you would be left with a remnant radiation. Their prediction was about 5 degrees above absolute zero, and this has now been observed. It was observed in 1965. It's at 3 degrees above absolute zero, very close to that first prediction. And the steady-state theory really can't explain that. Then there is the story of how the chemical elements are made. The chemical elements are made from the simplest element, which is hydrogen, by crashing them together and building up nuclei of bigger and bigger atomic weight through nuclear reactions. And most of that goes on inside stars, and I'll have a bit more to say about that in a minute, because the major person behind that was Fred Hoyle, other colleagues of his, particularly William Fowler in America. But that theory couldn't account for the amount of helium there was in the universe. Now, Gamow and his colleagues thought they could build up the whole periodic table from nuclear reactions which took place in the Big Bang. In the Big Bang, you would also had the right conditions, high temperatures and so on, for the elements to be formed. And it turns out that the upshot of all this research is that in the Big Bang you can only make helium and 1 or 2 other lighter elements. You can't make all of the rest of them. But you can't make enough helium inside stars, so you've got a very neat picture of how the whole periodic table is built up. And it requires the helium to be built in the Big Bang. Then, if you were a steady-state theorist, you would expect the universe to look the same as you looked to greater and greater distances away, which is looking the same thing as looking back in time. And you find that the universe doesn't look the same, that there are more active galaxies at the largest distances, i.e. further back in time you look. And indeed, already this kind of data was coming in the late 50s, early 60s, from observations of Martin Ryle here in Cambridge, that the numbers of galaxies, which should be uniform throughout space and time, is not. So the steady state theory is dead, buried, essentially, and the Big Bang reigns supreme. But that doesn't mean to say there aren't a lot of questions still hanging in the air, and we'll come to some of them. Okay, back to Hawking for a minute. And in this book, he has an interesting statement from St. Augustine that time is a property of the world that God created, and time did not exist before the creation. Extremely interesting statement from a great Christian theologian. But Hawking's take on it is quite bizarre. Hawking says that is a possible model which is favoured by those who maintain that the account given in Genesis is literally true. The Big Bang theory is more useful even though neither model is more real than the other. Well, this is in model-dependent realism. Model-dependent realism gives you the bizarre notion that the Big Bang theory and a literal reading of Genesis of a six-day creation 6,000 years ago are both possible models. And neither is more real than the other. That is astonishing. Possibly even more astonishing is his interpretation of Augustine, that this is a model favoured by those who take Genesis literally. The Augustine statement, of course, Augustine didn't take Genesis 1 literally, and into the bargain, that statement is entirely compatible with the Big Bang theory, of course. Time and space go together. That's precisely what the Big Bang theory says. They come into existence together. So we have some rather odd. It's not the only place where Hawking makes odd statements when he connects with theology, but that is particularly strange. It is interesting, I think, to think about what theologians have said about the creation. Here is Clement of Alexandria, a bit earlier, about 200 or so AD, a bit earlier than Augustine. He said, and how could creation take place in time, seeing time is born along with things which exist? Very similar kind of idea. And of course, Augustine. This is an interesting picture of him, by the way. I saw this in Florence a couple of years ago, and you see he's surrounded by sort of astronomical instruments, so he's portrayed as a scientist. Augustine said, as Hawking had it, there can be no doubt that the world was not created in time, but with time. So this intimate relationship between time and space. Time is created for Augustine. He said that we should therefore say that time began with the creation rather than that creation began with time, that both are from God, for from him and through him and in him are all things. And as I say, Augustine didn't take the days of creation literally. He thought that the creation happened all at once in the beginning, and then there was a kind of unfolding, a kind of creation making itself, as it were, as Kingsley said in the 19th century. That was exactly the view that Augustine took. Let the earth give forth, after all, it says in Genesis chapter 1. So the earth has that potential to bring forth that God has implanted in it. But it's all done under of course, the supervision, the direction of God. God is involved intimately every moment for Augustine and the great theologians of the church. Now, let me just sort of give you a flavour for what we're talking about in cosmology. That is a typical galaxy containing 100,000 million stars, and there are something like 100,000 million galaxies in the observable universe. And these clusters of galaxies are all moving away from each other as the universe expands. So it gives you sort of the scale of things. That is I think, a particularly inspiring picture. It may not look very much to you, but all these little blobs are galaxies, and indeed these are the earliest galaxies to form in the universe. This is taken with the Hubble Space Telescope. It's the Hubble Ultra Deep Field, and these galaxies formed some 13 billion years ago, when the universe was 5% of its present age. I think that is actually a stunning picture. I've mentioned that the chemical elements, the vast bulk of the chemical elements, are built up inside stars, and the way that these chemical elements get out into from the stars, so that planets and ultimately life can form, is through supernova explosions. The most massive stars explode as supernovae. This is a famous example called the Crab Nebula, first observed by Chinese astronomers in the year 1054 AD. And again, a beautiful picture of that from the Hubble Space Telescope. And so what happens then is that subsequent generations of stars can also have planets, because that material for planets has been built inside the cores of the earlier generations of stars. Okay, so what about the special nature of the Big Bang, of the universe then, that I've been talking about, the fine-tuning? It seems that the universe has been set up in a very special way, and that relates to two kinds of feature of the universe. First of all, the initial conditions back at the Big Bang. Now, the earliest time we think we can speak of with any confidence at all, or sense at all really, is, believe it or not, 10 to the minus 43 seconds from the beginning. 1 divided by 1 with 43 noughts after it, that fraction of a second from the beginning, when you'll be interested to know the physics that we can understand runs out. Now, I think it runs out a bit before that, to be honest. But certainly the point about that particular time is it's when we need a theory which combines the expertise of John Polkinghorne with particle physics, quantum theory, with the theory of the very large, general relativity, the theory of space and time, Einstein's theory. We don't have a valid or validated theory for that at the moment. There are 1 or 2 candidates, and one major candidate I will come back to, and that, of course, is Hawking's M theory. Now, but the other thing that is very special is the way that the physical constants seem to be set up. These are the constants that go into the laws of physics. They are the strengths of the various forces of nature. They're the masses of the fundamental particles, and so on. And these have to take very particular values. The ratios have to be just right. Conditions have to be just right in order for the universe to evolve as I've described, to make stars and galaxies in the first place, to make planets and ultimately life. And I'll give you a couple of examples in a minute. But of course this is an insight that has come out of cosmology. This isn't theologians here, this is cosmologists, and here is one of them, Paul Davies, who is very impressed by this. He is not a believer, but he has said that, like the porridge in the tale of Goldilocks and the 3 Bears, the universe seems to be just right for life in so many intriguing ways. He's written a book called The Goldilocks Enigma. It's one of his many books. And I've had the privilege of debating with Paul Davies. He's a great character, someone you can certainly talk to, and who is impressed by this so-called fine-tuning. Okay, well, let me give you at least a couple of examples right away. Now, one relates to that very beginning time, and the density at that time of the stuff, the matter energy of the universe, has to be what it is, to 1 part in 10 to the 60, in order for the universe to evolve in the way I've described. The universe is actually sitting on a knife edge. It's sitting on a knife edge between expanding forever and ultimately recontracting. It's the same knife edge between having a universe that's finite in size and a universe that's infinite in expanse. And what that depends on is whether gravity will be strong enough to pull it back in and recontract, essentially, or whether gravity is not strong enough. And there's a critical density of stuff. If the universe is slightly below that density, then gravity won't be strong enough to pull it back. It'll expand forever. And on the other hand, if it's just overdense, then it will be pulled back. Now, the universe needs to be sitting on that knife edge in order for it to give rise to galaxies, stars, and life. Otherwise, it will either expand far too quickly for anything interesting to happen, galaxies to form, or it will recontract before anything interesting has had time to happen. Yeah, 1 part in 10 to the 60 is something like the accuracy you would need to fire a gun at a coin situated in one of those galaxies I showed you a couple of slides ago, 13 billion light years away. That accuracy, it needs to be right even at 1 second from the Big Bang to 1 part in 10 to the 15. It's a very, very fine degree of accuracy that is required in the way the universe is set up at the beginning. Now, I've talked about these nuclear reactions that happen inside stars, and of course if you imagine yourself as making a universe that's going to have life in it, you would need certain constituents, carbon, nitrogen, oxygen, and so on. And the way carbon is made is by crashing helium nuclei together. You need 3 of these helium nuclei to crash together to make a carbon atom. And the problem is that if you've just got 2 of them, that's beryllium, and it only exists for a tiny fraction of a second. It's unstable. So what you need for this reaction to work is an enhanced effect. The very fascinating thing about this is that it's none other than our friend Fred Hoyle, the atheist astrophysicist, who discovered this enhanced effect. He predicted that there was a certain thing called an energy level, a resonance in the carbon atom at a certain energy, and there had to be that in order for this reaction to go the way it did. And that's related to the strength of the force which holds nuclei together, the strong force of nuclear physics. There's a story which I don't go into too much detail about here, but no one had observed this energy level. So Hoyle informed colleagues in America, and they, took him rather lightly at first, but then did go and make the measurements, and they discovered Hoyle was right. William Fowler, one of the Americans, got the Nobel Prize. Hoyle was omitted. He did not get the Nobel Prize for this, and many thought that was unjust. And indeed, in St. John's College Library here, there's a really wonderful and touching letter from Fowler to Hoyle, which is deeply apologetic and incomprehending about Hoyle missing out on the prize. And actually, just as an aside, William Fowler used to live in the same street I live in Cambridge. That's fame by association. But Hoyle, when he made this discovery, was moved to make this remark. A super intellect has monkeyed with physics, as well as with chemistry and biology, and there are no blind forces worth speaking about in nature. This is a man who made broadcasts on the BBC in the late 40s, early 50s, describing religion as an illusion. His science forces him to talk about a super intellect behind the universe, essentially. Okay, now why might we then go from office? Well, what are the explanations for this fine-tuning? You see, the one might naturally go for, and of course probably in this room we'd be inclined to go for this kind of explanation, is that God had intentions and purposes of bringing about a universe with life in it, with intelligent life, with creatures who'd be able to relate to him. But that is not an explanation that many scientists like. So what are the alternatives if you are an atheist? Well, one of them is to say, you're wrong. All these numbers you're talking about really couldn't take different values. The strength of the strong force of nuclear physics, all those forces have to take the values they do, and if we might one day get a more fundamental theory, so-called theory of everything, which would calculate all those numbers. It's rather interesting that Einstein was a person who was looking for such a theory. But during his search for the theory, he expressed it by saying, what I'm really interested in is whether God had any choice in making the universe. It doesn't preclude God, rather restricts God's choice if there's only one set of physical laws that's possible. And connected with that is the idea that, well, maybe the universe could have started off in any way and it would have given the same end result. Well, the alternative is diametrically opposed to that, and it's to say that there is a multiverse, a vast collection of universes, usually taken to be infinite, and the idea is, well, that if all these constant initial conditions do vary, but in lots of different universes, then you're bound to get something like our universe cropping up amongst this ensemble, where the conditions turn out just right, and well, of course, that's the universe that we inhabit. We couldn't exist in any of the vast majority of other universes where the numbers are wrong, but we could exist in this one. Okay, so I will come back. I mean, it has to be said that this is the most popular now, it looks rather implausible that there's only one set of self-consistent laws, but before going more into that, let me come back to what I mean by an ultimate explanation. Why is there something rather than nothing? That's the basic question. And Hawking thinks he can answer that question too. This is thought to be in the preserve of theology and philosophy, but Hawking thinks he can answer that. He says a number of things in this book. We create the history of the universe by observing it. He says that all possible histories of the universe occur. These are ways of getting from state A to state B, all of them occur. And we select a set of histories, no matter how improbable, which are compatible with our own existence. These are some rather bewildering statements, and I'll come back to them in a minute. He also says that negative gravitational energy cancels out positive matter energy. So that enables the universe to create itself out of nothing, because there is basically nothing. And then he says that M theory predicts a great many universes were created out of nothing, not just one. And then he adds into this mix something which appeared in his first book, A Brief History of Time, called the No Boundary Proposal, where time becomes imaginary in the earliest epoch. Let me talk about that last one first. By saying that time becomes imaginary, it means it becomes like a space dimension, like another dimension of space. Now, I think traditionally, if you had a quantity in physics which you calculated that turned out to be imaginary, you'd think you'd got something wrong. I mean, imaginary has a technical meaning in mathematics here for anyone who knows about such things, square root of -1 and so on. But you'd think you'd got the answer wrong. I mean, it can be used as an interesting and useful calculating device, an imaginary number, but not for a quantity that's out there in the real world to be measured. But Hawking, of course, is a model-dependent realist, and he says it's meaningless to ask which is real. The real time, of today, subsequent to the Big Bang, or the imaginary time in the earliest period, if that word period has any meaning. Now, I think there are severe problems with this, scientifically. And perhaps one of them is, if time becomes another space dimension, how does time ever get to flow? Time is something which measures change from one point to another. What about some of the other claims on the list? M theory predicts the creation of a lot of universes out of nothing. Doesn't require the intervention of a supernatural being or God. These multiple universes arise from natural law. Well, there's no mention in the book of the highly speculative nature of this M theory, which is actually a generalization of something called string theory, if any of you have read any of the sort of popular literature on this. There is no evidence for M theory being true, no observations or experiments which have been done, and serious questions have been raised over it. You wouldn't realize that from Hawking. But then, the whole idea that the universe can create itself out of nothing is, of course, deeply flawed. And of course, for Hawking, it's because negative gravitational energy cancels out positive matter energy. Okay. I have, for the sake of argument, a £100,000 mortgage. I have a house which I purchased for £100,000. The two cancel out. Nothing. Does that mean I've created a house out of nothing? I mean, if there is really nothing, then there will subsequently be nothing. And I think part of the problem is the misleading way this word nothing is used. It's often used to be synonymous with the word vacuum. And a vacuum in quantum theory is frankly not nothing. It's not even empty space, because it's a hive of activity where particles constantly are coming into existence and going out of existence, being created and annihilating in a fraction of a second. And so in a sense you can borrow energy from the vacuum. These other ideas, we create the history of the universe by. So you can see how he gets these ideas from quantum theory, the first two on here. Because a famous physicist called Richard Feynman used the idea of multiple histories as a calculating device. But of course, for Hawking was a model-dependent realism. These are as real or as anything else. You can think of them as real, or if they're useful for calculating, or if they're useful, you can imagine them as real. But we don't have to take that line, of course. We don't have to consider all the possible histories of the universe as occurring. Now, it seems to me that when we ask this question, why is there something rather than nothing, only God can provide this. And I'm taking you back now to St. Thomas Aquinas here, who thought that because God in Christian theology is a necessary being, and the universe in contrast is contingent. So let's explain these terms. Necessary means cannot but exist. There never was when God was not. God is eternal. He cannot not exist. And that is part of the concept, what we mean by God. The sort of question that someone like Richard Dawkins raises, well, who created God then, fails to understand the meaning of the term God, because anything created is not God. We can, of course, debate whether a necessary being exists, but if a necessary being does exist, then that being explains why everything else exists. Because the universe is contingent. That means that the universe may or may not exist and could be different from what it is. John mentioned the term contingent in that latter aspect. It either exists or doesn't exist. Why it exists, it may not exist. It is contingent. It doesn't have to exist. And that is what has generally been thought about the universe by philosophers. And the interesting thing is that this has been recognized by physicists. Not least, it was recognized by Stephen Hawking himself back in A Brief History of Time when he posed this question, rather beautifully, I think. What is it that breathes fire into the equations and makes a universe for them to describe? Exactly. You can have the most wonderful theory, but why is there a universe which that theory describes? Martin Rees, who is Astronomer Royal, Master of Trinity College, has given up being President of the Royal Society. Great cosmologist. He says the same thing. Such questions, why is there something rather than nothing, lie beyond science. They are the province of philosophers and theologians. Okay, and interestingly enough, this man, who was this is Dennis Shum, another great cosmologist. He was the supervisor of both Hawking and of Martin Rees, and here's a bit of more fame by association of Rodney Holder. He said, none of us can understand why there is a universe at all, why anything should exist. That's the ultimate question. Science simply does not answer that question. And none of these three I've just put up here are believers. They're all atheists, Hawking, Rees, and Sharma, but they recognize, at least Hawking did recognize, that point. Okay, now, okay, so neither of these strategies explains why there's something rather than nothing, but there are problems with each of them in explaining why the universe takes the particular form it does. They might not, okay, they might not explain why there's a universe at all. Do they explain why the universe takes the form it does, why it's so special, why it's fine-tuned? Well, if there's only one self-consistent set of physical laws, the problem there is, why does that set of laws give rise to life? It could give rise to almost anything you can think of, some amorphous lump of rock or something. Why does it give rise to the rich complexity of the universe we observe? And for the multiverse question, or solution, well, why this multiverse? Why not another different kind of multiverse? Why a multiverse in which one or a small fraction of its members give rise to life, the vast majority don't, as opposed to another multiverse, another multiverse? So there are problems. Okay, let me just give a brief history of cosmology. Back in the late 60s, a group of cosmologists tried to show that however the universe started, whatever chaotic beginning it had, it would give rise to the smooth universe we see today with galaxies, stars, and ultimately life. And interestingly, the nail on the head for that one was hammered by none other than Stephen Hawking, who wrote a seminal paper back in 1973 with a colleague, Mary Collins, and he showed that from random starting conditions, the probability of getting a universe that looks like ours today, stars and galaxies and life, is 0. No chance. That doesn't mean to say that such a universe can't exist, in the same way that if you imagine a line between 0 and 1, and the probability of taking a pin and sticking it on this line and getting exactly the number of half, well, that's 0. That's 0. Doesn't mean to say the number of half doesn't exist. But Hawking, of course, went towards a multiverse as the solution of this problem. A single universe starting randomly, probability 0. If you have a multiverse, you thought you might do it, but it doesn't. For anyone who does have a bit of maths, if you have infinitely many universes, each with a probability of 0 of giving rise to life, the number which would give rise to life is infinity times 0, which is undefined. Okay. Now the next move, and this theory has got quite a bit going for it in terms of recent observations, some form of this theory anyway, called inflation. And the idea was that the way the universe started off, it could be forced into the right conditions if it had a very, very rapid period of expansion near the beginning. The first 10 to the minus 32 seconds from the origin. And then you'd get the sort of normal Big Bang. Now, the problem with inflation was that it itself needed to be fine-tuned. And of course, this is in a sense always the problem. You get a better theory, but that theory has free parameters that you need to set. You'll never quite get into the ultimate theory, which has no free parameters. So the answer to that from certain cosmologists, notably Andre Linde in Stanford in California, is to go for a multiverse version of inflation. So you end up with a vast, infinite universe, if you like, but with lots of different regions which inflate or don't at different rates and so on. And you get universes starting off from within those bubble universes and bubbling off, so you get a gigantic collection of what are called individual universes. They're really part of the same overarching space-time, but this gets called a multiverse. And that's the most popular form of the multiverse today. Then there is something called string theory, and M theory, as I mentioned, is a generalization of that. You don't really need any of the details here, but the idea is the fundamental particles, the fundamental building blocks of the universe are not point particles, but they're tiny, tiny bits of string, which really very tiny, below any observational threshold, and the ways in which these strings vibrate gives you the different particles. And it was originally thought that string theory was the ultimate theory of everything. The idea of it, to begin with, was indeed to calculate all the constants of physics. After 30 to 40 years, it has not calculated anything. And so that's now seen by some, Leonard Susskind in particular, one of the pioneers, as a strength. Okay, string theory has maybe 10 to the power 500, 500 naught of different solutions. And maybe these all exist in different universes. And possibly the neatest way of thinking about this is to combine it with inflation, so that the different universes that arise out of inflation have different, are characterized by different versions of string theory, if you like, different solutions to string theory. Now, running out of time, just to mention that there are lots of other theories out there, something called conformal cyclic cosmology. The use of the ideas of collapsing, expanding and collapsing universes, but this is run rather differently to Roger Penrose, but he does say that the universe goes back to the same state as it started from and then starts again. There's something called ekpyrotic cosmology. You've all done Greek, of course. That's the Persians, out of the fire. But this is about higher dimensional spaces colliding with each other and creating big bangs. There's lots of theory out there. And one of the things that is often said about cosmology today is that cosmologists are often in error but seldom in doubt. And it is a case, I think, of theory outstripping experiment and observation, which is a point I will come back to as I now move on to look at multiverses. And there are a number of problems. It is important to recognize that the physics is speculative. 10 to the minus 43 seconds, that's the era. To reproduce the kinds of energies pertaining at that point, you wouldn't need a Large Hadron Collider as at Geneva, you'd need an accelerator the size of the galaxy. The Large Hadron Collider is a wonderful instrument, and that's taking us back to maybe the first billionth, as 10 to the minus 10 seconds or so from the Big Bang, and recreating those kinds of conditions. Tremendously exciting, but a long way from the realm where string theory and theory applied. Martin Rees, whom I mentioned a while back, in one of his books says he is a cautious empiricist. And he says that that means that he accepts the physics applying to the universe from its first thousandth of a second from the origin, from t equals 1,000th of a second up to t equals 13.7 billion years. Now, I mean, that may surprise you. That might sound extraordinarily, might sound arrogant even, but it's not. I mean, the physics is well known. I mean, these nuclear reactions I was talking about take place in the first seconds and minutes of the universe's existence. We know the kind of, when we can reproduce those sorts of conditions. But nevertheless, Martin Rees opts for a multiverse because he wants to avoid the need for God. He recognises why is there something rather than nothing problem, but he still wants to go for a multiverse to solve the fine-tuning problem. There is a problem about actual infinities in nature, a number of paradoxes. I mean, one point is that you can never complete an infinity. You can always add to an infinity. And why does this particular infinity have the property that you require of it? I mean, here's an infinite set, 1, 3, 5, 7, 9, 11, they're the odd numbers, but none of them has the property of evenness. Why should the universe have the property that it is conducive to the existence of life? I mean, another problem is about human identity. If we are in a universe, a multiverse, there will be many copies of this room, copies of you and me. There'll be some copies in which I thought it would be much pleasanter to have a lie-in this morning, stay at home, not bother to come into the Faraday Institute, whatever. There'll be others where I just sort of drop down dead halfway through giving the lecture. Indeed, anything I could do, or any decision I could make, will be made by some version of me in another universe. And that might not defeat the idea of there being multiple universes, but it is, if we can do with a theory that doesn't have that phenomenon, I think we would be better off. And for that kind of reason, the problem with infinities and so on, I think this is not a simple hypothesis, but a complex one, and physicists usually go for the simplest of competing hypotheses which explain data. Multiverse seems to be the most complex thing you could go for. When you think about this infinite collection of universes, there'll be far more universes which are chaotic in some sense, which have odd features in them, which are not uniform and open to science, if you like, in the ways that John was talking about. There would be a lack of predictability, and indeed it might be a discouragement to do science, because suppose we could do science, but then we started finding certain odd features in our laboratory, we could sort of give up and say, well, maybe we're just in a multiverse with those kind of odd features happen. They do in some universe. Why bother to find an explanation within scientific laws as applying to this universe? Now, there's an interesting one to do with the cosmological constant. This year's Nobel Prize for Physics, interestingly enough, went for some physicists who discovered that the universe is accelerating. Back in the late 90s, they discovered that this expansion of the universe is not slowing down, but speeding up. So it's accelerating. Now, that takes us back to Einstein, something called the cosmological constant, which Einstein originally included in his equations. He did it in order to get a static universe, a universe that was eternal, and so on. He set it to a particular value so that to avoid a universe that had an origin and so on. He later called it his biggest blunder. Lemaitre, whom I mentioned, did have a cosmological constant too, but at a more general nature, didn't take particular value. In fact, it was a free parameter which could be set to match the way the universe evolved. Now it's been discovered that there is such a thing. And what it is essentially a repulsive force. And physicists think they know what it is. It's the energy associated with the vacuum, which I mentioned. The vacuum is far from nothing. It has an associated energy. The trouble is, when physicists calculate the value of the cosmological constant, they get a value that's 10 to the power 120 times too big. There needs to be some factor which cancels out that to 120 significant figures. Phenomenal fine-tuning. Well, there may be a multiverse explanation for that. And indeed, I mean, someone called Steve Weinberg thinks that he's close to having a multiverse explanation for that. But it's certainly contentious. Paul Davis, for example, doubts that. Okay, now fine-tuning is still required to get a multiverse in the first place. You need, in order to get this overarching space, which is the most popular way of getting multiverses, you need the mean density of stuff, which I was talking about earlier on, to be less than the critical value. So it needs to be between naught and this critical value. Now, it could be in a vast range, and you could end up with a finite universe rather than an infinite universe. One of the problems there is we don't know what the mean density of the whole overarching space-time is. We can only measure the density within our patch, if you know. So it might be higher than the critical value, and we're in an underdense part, or vice versa. We simply don't know and have no way of knowing unless there's only one way we can really know that, and that is if we were in a relatively small, finite-sized universe. And there was some evidence a few years ago that might even be the case, but I won't expand on that. So it's controversial. There's a question about the amount of order there is in the universe. Roger Penrose in Oxford calculated that the universe needed to be started off highly ordered in order to give rise to the order and structure that we see. Because the universe is winding down in the sense that it's going from states of order, high order, to low order. This is the so-called second law of thermodynamics. If I knocked that cup of water over, well, it's plastic, I wouldn't actually break the cup, thankfully. The water would go all over the place. But what you do not see is water that's diffused into a carpet, sort of coming back into a cup and jumping back up onto tables. That's not the way things happen. We're going from order to disorder. So, Penrose's calculation is that the creator, as he puts it, metaphorically, but the creator had of the order of 10 to the power 10 to the power 123 universe configurations to choose from, only one of which would have given rise to the order and structure that we see. And, well, 10 to the power 123, one with 123 noughts after it, 10 to the 123, one with 10 to the 123 noughts after it. That's pretty incredible fine-tuning. But there's even something more to say about that. If you wanted to create a universe with life, you could do it by simply crashing together the matter in the size of about the solar system randomly, and getting you'd have, if you like, 10 to the power 60 configurations to start from, one of which, by random collisions, would have given you a solar system with life, planets and life and so on. Now that's a pretty remarkable amount of fine-tuning, 1 in 10 to the 10 to the 60. But it's swamped by the 1 in 10 to the 10 to the 123. Now if I've lost you completely, it wouldn't, it would be, understand it's quite a technical point. This is the perennial monkey sitting at a typewriter. Okay. Suppose the monkey coming up with to be or not to be, that is the question, is a universe that corresponds to life. Then, okay, eventually the monkey will come up with to be or not to be, that is the question. The problem is, we're not in that universe. We're in a universe that corresponds to the complete works of Shakespeare in terms of its order, and so on, by comparison. So there will be far, far, far more universes, thin on the ground, but which correspond to be or not to be, that is the question, than which correspond to the complete works of Shakespeare. That's the kind of analogy. Yeah. Okay, some people think that if there's a multiverse, we'd be more likely to end up in a simulated universe, like in the film The Matrix, than in the real universe. I will not dwell on that. It's because once you get intelligent civilizations, they start creating universes, and it's much easier to make simulations than real ones. Paul Davies is someone who takes that seriously. I mean, John Barrow here in Cambridge, and philosophers you'd imagine in Oxford, called Nick Bostrom. Anyway, a multiverse as an explanation for the universe and its fine-tuning seems, well, it doesn't provide an ultimate explanation. It seems complex. It doesn't explain why there should be life. And this universe looks rather too special from that Penrose analogy. And God, I think, does explain why there is something rather than nothing. God does explain why there should be life, because God would have purposes and intentions for the universe, and why God would be more likely to create a special universe than one that's sort of just good enough, so to speak. And here's Georges Lemaitre, back to him again, and what I think is a lovely quote: "There were two ways of arriving at the truth. I decided to follow them both." Cosmology and theology. Okay, well, I stop at that point and take some questions. I haven't completely overwhelmed you with technicalities, big numbers. Yeah.
One thought, looking back to John Polkinghorne's introduction about and the discussion about God of the gaps. Isn't there a danger that this is a very complicated argument for the big gap? Is it still not possible that the other alternatives may be real?
Yeah.
But that doesn't mean there is no God.
Yeah, that's true. And that's a very good point. With regard to the first one, is this a God of the gaps argument? I think it's not a God of the gaps argument because what the question we're asking here, I think, in John's terminology, would be a meta question. It's not about the processes of nature, and as in intelligent design, that bacterial flagellum is too complicated to be created by evolution or whatever. It's why do the laws of nature take the form the laws of nature do? Now, generally what you do in physics is you discover what the laws of nature are, and to describe a system you say, well, how does it behave given these laws, these initial conditions? What we're doing here is asking why the laws are as the laws are, which I think is a meta question. Now, of course, it is the second part of your question. Of course, it is perfectly possible that there is a multiverse. And indeed, there are some Christians, philosophers, theologians, scientists who are in favour of there being a multiverse. Now, you might think, well, actually, God is highly creative. God might create more than this universe. Why doesn't just create this one? And so on. And I could name some people. I mean, Don Page is a cosmologist. He's a conservative evangelical colleague of Hawking. He's written a lot with Hawking on papers, and he's in favour of a multiverse. The late Arthur Peacock, pioneer in the science-religion discussion, he thought, well, what matters is that the multiverse itself gives rise to cognizing subjects, as his expression, that there are intelligent creatures somewhere in the multiverse. It doesn't matter that there are other dead universes, as long as there's a universe with life in it. Now, Keith Ward is an interesting theologian, and I would go along with Keith Ward in what he says about this, that God could in principle create lots of universes, but he wouldn't create universes that were overwhelmingly evil, or with a preponderance of evil in them. Now, whatever you think about the theodicy question and the quantity of evil in this one, you can imagine universes in which there is far more evil. So that would be his reservation. I suppose the problem is that what's on offer scientifically makes no comment about that, and it makes no sort of kind of reservations about those universes. I think, I'm a skeptic about multiverses, particularly with the various theories that are knocking around. The argument would still apply. The fundamental argument would still apply, because you'd have this why this multiverse question. The only way of avoiding the why this multiverse question is to go for every possible universe exists. Not just, there's a multiverse, might have infinitely many members, but there are lots of other possible multiverses. All of them exist in some fashion. And I'm not sure that's even a coherent, possibility. I mean, I talked about identical copies of me, but really they are copies of me. They're not me. I make the decisions I make in this universe, and a universe in which I make other decisions is not, doesn't exist. The universe in which I decided not to come this morning doesn't exist. A copy of me may have done that. So I think there are incompatibilities when you start to think about that idea. I think it's the only one you can go. I mean, there's a cosmologist, Max Tegmark, who goes precisely that route, and he says all mathematical structures have physical existence. Well, you can even then start to think about whether universes have to be described by mathematics. Whether that is a total constraint. But that's certainly a good question. Okay, sorry. Yeah.
Following on from your answer, if you're saying, if we're saying that that there is a God rather than a set of multiverses, or the question of God is a better explanation of multiverses for why there is life in the universe. It seems to me that the converse of that is that you're saying if we're not trying to wrongly answer a scientific question like this, the converse is that you're saying that scientists, by proposing a multiverse, are trying to answer a religious question, that science is moving into religion, that basically the scientists they're saying, oh no, we're going to have to believe in God unless we can find a better explanation, so they're coming up with this explanation so they don't have to believe in God. And I just wonder if you have any comments on that. It may or may not be conscious, but I'd be really interested to know if you think there are scientists who do it consciously, that they kind of have to find something so that so they aren't faced with the need to believe in God.
Yes, that's very interesting, and I think that it is the case that some consciously adopt a multiverse. So I mentioned Martin Rees. I mentioned earlier on Leonard Susskind, and I had the great privilege of being at this conference. We invited a symposium in Stanford a couple of years ago where Susskind is working, and Templeton are very good to you. They sit you, give you a nice dinner beforehand and everything. And I was sitting next to Susskind, and he said, "Oh, I've got this book coming out." I can't do the American accent, but I've got this book coming out, and it's called The Landscape of String Theory and the Illusion of Intelligent Design. And he says on the last page of this book, I say, well, God, if she exists, has made herself totally redundant. Okay, and indeed, this book is out. With something like that title, I've got the exact title. So he is someone who deliberately goes for this theory as seemingly defeating the need for God. You wonder about Stephen Hawking with regard to this too, whether he's really opting for this theory with a metaphysical preference. I mean, going back to Hoyle, he had a metaphysical preference for the steady state theory, which he was one of the pioneers of, along with Bondi and Gould, who were also, interestingly, atheists. And Bondi, another steady state theorist, was the president of the British Humanist Association. Serious atheism. And it does tend to colour the science in some ways. Now, that may or may not matter, because in science things tend to get ironed out ultimately at the bar of observation and experiment. The problem with multiverse theories is, and indeed, I'm not the only one. If I were the only one to question them, I'd be worried about myself. But there are serious questions about whether string theory, M theory, is science or whether it is metaphysics. There have been 2 books come out in the last couple of years seriously questioning this. There's one called The Trouble with Physics by Lee Smolin, and another one called Not Even Wrong by a chap called Peter Voigt, W-O-I-T. The title Not Even Wrong is quite amusing, because there was this very famous physicist called Wolfgang Pauli, who used to sit at the back when a poor research student, postdoc, was just giving his seminar paper. And at the end, Pauli would get up and say, "That's wrong." And then there was one poor chap who one day, Pauli got up at the back and said, "That's not even wrong. It's not even worth discussing, it's so bad." But anyway, but anyway, both these books are seriously critical of string theory, string M theory as science. Now, on the other hand, it has to be said that this is highly sophisticated stuff. This is mathematically incredibly complicated and technical. And there are a lot of people working on it. Part of the criticism of Voighting is that it's become a sort of sociological thing, a bit like Kuhn and his paradigms. If you want to get on in theoretical physics, it's a kind of trendy thing to do. But anyway, there is a lot of work done. Maybe it'll prove to be the ultimate theory, but it does need to get a more serious handle on making predictions and getting them verified before it can be recognised. And then whether it gives rise to multiverses or not, we can never ever observe other universes than our own. That's which is a serious objection, I think. They're beyond. No signal can reach us from other universes. So in that sense, they will remain metaphysical. Yeah.
If, as Hawking offers, that all possible histories of the universe occur, were those staggeringly enormous numbers you offered a refuge?
Yeah, in a sense, these are. You mean, are they a refuge from what? From
Well, for theists.
For a refuge against theism, or
Well, no, I mean for the theist, because if all possible histories of the universe occur,
yeah.
and we just happen to be experiencing the one in which life has been realised,
Yes.
the numbers, as enormous as they are, seem irrelevant.
Yes.
I mean, have we actually answered that explanation? Have we counted it?
I'm not sure I'm quite following. I mean, basically Hawking is saying that all possible histories exist, okay, so that they're real in some sense in his model-dependent realism, which is debatable whether it is real. Okay. We pick out one in which, which we exist, and in a sense, the fact of all the histories makes our existence possible in the theory if they're all real. I suppose that's basically the idea. And indeed, on any of these multiverse theories, the other universes have to be physically real in order to do the job of making our existence possible or probable. Now, I mean, one thing just to throw into the pot is an argument that occurs in Keith Ward's nice little book, Why There Almost Certainly Is a God. And that is, okay, suppose all possible universes exist. How about a universe with God in it? That must exist. Now, God is a necessary being. Necessary being means God exists in all possible universes. There you go, God exists in this universe. This is a kind of variant of the ontological argument. And in fact, it's a valid argument. Provided you take the premise that God's possible in the first place, I think. I think multiverses tend to be used as a refuge of the atheist, but they're certainly not incompatible with theism.
Would that be the same God?
Oh, I think so. And now we can get into. Actually, I did have a question raised a few weeks ago. It was enough at a diocesan conference about the same God or the Islamic God in another universe.
But if there are all these vast panoply of multiverses, this is the one that we happen to be in.
Oh yes.
Isn't that rather inefficient?
Yes, I think it could be regarded as inefficient. Though, on the other hand, you could say that our coming into existence in this universe is inefficient to some degree. I mean, you've got all those trilobites in the Precambrian or whatever. You've got a lot of avenues that prove unfruitful in this long process of creation and making itself, creatures make themselves and so on. So there's a certain amount of waste in producing intelligent
Yeah,
creatures.
but it's not got 10 billion noughts on the end of it.
It's not on the same scale. That's true. That's true. And I think that would be an argument for a theist. That would be somewhat troubling. Yeah. Yeah.
This is just a matter of interest, really. But you were saying how incredibly unlikely it is. The incredible chances against there being a universe that has got life in it. What does that mean for life in other parts of this universe?
Oh yes. Yeah.
Is it just it? Yeah. Do you think there is now? Given that we exist in this universe, does that mean that it's probable that there's life in other parts of this universe?
Oddly enough, I've got a few questions for the last session of the day to sort of discuss the groups, one of which is about extraterrestrial intelligent life. But just to make the point at this moment that all these conditions I've talked about are conditions for anything interesting at all to happen. So they don't preclude the existence of life on other planets. A few years ago, there was a character called Frank Drake who wrote down a famous equation, Drake's equation, with lots of probabilities multiplied together, which was supposed to calculate the number of civilizations there were in our galaxy and so on. The trouble is we don't know what these probabilities are. Now, there are 10 to the 22 stars in our observable universe. We started observing planets and so on around some of the stars, some even at the right kind of distance from a star, like a side, all that kind of thing. So, well, does that up the probability that there's life? What we don't know is what the probability of life coming into existence in the first place is. If it's less than 1 in 10 to the 22, yeah, you know. But if it's 1 in 10 to the 150 or something, what we don't know is what that probability is. But there's a lot of research going on. I mean, and some of the research even on Earth with these deep ocean sort of hot points and so on, bacteria and life forms, which might have relevance to that kind of discussion.
I recall reading that the position of the moon relative to the Earth is critical for stirring the mulch that created life.
Yeah.
Had it been any closer, it'd have been too rough.
Yeah.
Had it been any further away, it would have left.
Yeah, exactly. There are these kinds of, all this stuff sometimes goes under the name of anthropic principle. And of course, as Greek scholars, you will know the derivation. In fact, it probably ought to be called the biophilic principle. But, it's life-friendly conditions rather than specifically human life conditions. But, yeah, what I haven't gone into is those anthropic kinds of conditions which apply, more locally, and there are quite a number of those as well as the cosmological ones. So, yeah, so even if you get a planet at the sort of right mass and distance from its parent star and so on, there are a lot of other factors that have to go into it for it to be a life-bearing planet. Yeah.
Just a mid question, a big subject. So we talked about time, the understanding of time. I'm just wondering, in what sense, if time is very variable depending on the gravitational pull and various other things, to talk about the age of the universe as being 13.7 billion years.
Yes.
Isn't there a sense where that's a meaningless
measurement? There is one sense, of course, in which time is relative, and in Einstein's sort of special relativity, different frames of reference moving relative to one another, clocks will go at different rates, all that kind of stuff. But there is an overall cosmic time, and there's a frame of reference against which we can measure that cosmic time. It's basically the one against which the stationary relative to the background radiation in the galaxies and so on. So there is a cosmic time which has a definite meaning, and that is 13.7 billion years. Though with Hawking's sort of imaginary time idea, it gets a bit fuzzy very near the beginning, when real time and imaginary time sort of mesh when we do that, which is a sort of complicated issue. But yeah, but the 13.7 billion years does have a real meaning, and that, as John was right to point out, has been better and better defined as we've gone on from Lemaitre time. Lemaitre predicted an age about 2,000 million years of the universe, and Hubble, and those early measurements. And that was a big problem for quite a long while in cosmology, because we knew that there were certain objects within the universe that were older than that, probably clusters of stars and something. The Earth now is 4.5 billion years old. So, but that all got tidied up in the sort of 50s, 60s, and now the latest satellite